Recording? Okay, good. All right, thanks for coming, everybody. I'm happy to introduce our second speaker for the day, Michaël Poss. Michael is a senior researcher at the Centre National de Recherche Scientifique in France in the LIRMM laboratory. He obtained his PhD in 2011 at the Université Libre de Bruxelles with Bernard Forts, Martine Labbé, and François Douveau, and he currently focuses on robust combinatorial optimization. He's also the founding managing editor of a new journal, Open Journal of Mathematical Optimization, which promises very fast turnaround times, as far as you've heard, in terms of reviewing. So that's a free advertisement. And today he's gonna tell us about optimization problems in graph with locational uncertainty. So Michaël, please go ahead.
So thank you for the nice introduction and for giving me the opportunity of talking about this work. So this is a recent work that I've done with my colleagues, Marin Bougeret, who is also a professor at LIRMM, and Jérémy Homer, who is a professor at Rennes University. So we're going to talk about robust optimization. So I hope many of you have heard of it. So it's a framework to handle optimization problem when some of the parameters are uncertain. But here we're going to focus on certain type of problems. So we will assume that we have graphs. So here we have a unique graph that is described by the green edges. So the green stuff are the edges of the graph, and then you have those sets of dots. They look like polytops. They may be thought as polytops, but they're really set of points. Okay, so you have U1, for instance, that's one node of the graph. You have U5, that's another node of the graph, and then you have edge linking those nodes. Okay, so this is just one node of the graph that we're interested at, and this node has 5 points in it, in a sense. Okay, and so in this graph we look for feasible solution to combinatorial problem that we will define soon. So for instance, we would like to find a path from U1 to U6, okay, in the green graph. So one such path could be, for instance, this path. We take edge that goes from U1 to U5, and then we take the edge that goes from U5 to U6. We have only two edges. Okay, but then since we want to do optimization, we have to introduce the weight of the edges, the cost of the problem. So for that, we will use a robust optimization type of ID, meaning that we will take the worst position for every node. We will take the worst possible position of the node in that set, and then that will give us the weight of the total path. So for instance, here we could assume that the worst position for the three nodes that are taken by this path could be locating U1 here, locating U5 here, and locating U6 here. And then if we do that, the cost of the path would be the distance between the first nodes, the first pairs of nodes, and plus the distance between the second pair of nodes. Okay, so that means that actually I need to have defined a distance, which I didn't say before. So we actually have those distances given between any pair of points that we had in the plane. Okay, so we really want to find a path that minimizes the worst case distance, knowing that the adversary will choose the worst possible position of every node in its set. Okay, so that was kind of a hand-waving definition. Now we have a formal definition. So the type of problem we wish to solve is given by a graph, as I mentioned before. So the set of edges, the green edge that I mentioned before. Then we're looking at a family of admissible subgraph, F. So in my problem could have been, for instance, all paths between node S and node T in a graph, for instance. But it could be all spanning tree in a graph, all Steiner tree, all matchings, whatever you like. And then for every node, we have a finite uncertainty set UI. Okay, and then we also have distances that are defined for every pair of points in every couple of such uncertainty sets. Okay, so and then the problem we wish to solve is to find the cheapest admissible subgraph, given that the cost is to maximize over the worst possible position of the node in the set U. So because we have lots of min-max stuff in robust optimization, I will try to use decision variable in blue and adversary variable or uncertain parameter in red always. And so some of the results in the paper, they really like combinatorial optimization. So in that case, we like to use sets. So like you really try to find the best set, but some of the results are based on integer programming, cutting plane, those kind of stuff. So in that case, you like to have binary variables. So in that case, we would have variable X that tells us which edge actually belong to the set F. Okay, so you have, of course, xij equal to 1 if ij belongs to F. So it's really two ways of looking at the same problem. Okay, so that's the type of problem we will be discussing over in the next 20 minutes. So we have different applications for that problem. So actually, one application could be to extend the subway networks. So I have a friend that is working in Brussels at expanding the subway of the city, and they're building a new line 3. And it's taking decades because Belgium is a very complex country with many layers of government. So between the first plan and the last plan, many things have changed. In particular, they may not be able to locate the station exactly what they want because of many political or environment issues. So because the length of the line depends on the exact location of the station, you may consider that that's really a special case of the problem I just mentioned, where the set of feasible, the feasible subgraph would be, for instance, trees, or if it's a single line, it would be simply path. Okay, so that could be one application for the problem. Another application could be clustering. So in many problems with clustering, you have missing data. So you have upper bounds, lower bound on some of the component of the vector you wish to partition, but then you don't know more about it. So at the end of the day, you end up, instead of points, you end up with boxes, rectangles in higher dimensions. And you still wish to partition them efficiently, and so using a clustering algorithm. But in that case, well, one of the approach could be to use a min-max, a safe min-max approach, as I just mentioned. Okay, and so in that case, the structure of the subgraph would be union of cliques, because every set would contain every edge linking every pair of points that's in one set of the partition. Okay, so this is for the motivation of the problem. Now, we're not exactly the first to look at the problem. We're the first to look at in its full generality, as I just defined before. But if you consider, for instance, Euclidean distances, then you can actually, there's a very nice work that has been published a few years ago that could be applied. So here we assume that we have Euclidean distance instead of arbitrary distances. Then you can use some nice trick in robust optimization. So here you replace the two distances by maximization over norm1 ellipsoid. And then you can switch the summation and the maximization here. So you get here, okay? And then here, what do you do? Well, you can merge. No, you don't merge. Sorry about that. So here you swap the two max. So here the max was inside. Here that max gets outside, and this max here gets inside. And now, if you have so the set of 4 points that are allowed for every node of the graph that is a polytope. I will comment on that soon. Then you can. This is a linear program, because you just have the variable u, everything is fixed, x is fixed, w is fixed. So this is a linear program. You can realize it, and then you get this min-max-min, which is reminiscent of two-stage robust optimization that you can solve exactly approximately using dedicated technique that I will not detail. So for instance, affine decision rules. So just a comment here. Initially, in my introduction, I said that every node could take different value, which were sets of points. And here I'm using a polytope. But because the distance here is convex, it's actually equivalent to consider a set of points or a polytope that's its convex hull. Okay, so this is one kind of technique that could be used to solve the problem that I just mentioned. But typically, this two-stage problem is still very hard because it's a two-stage robust optimization problem with ellipsoidal uncertainty. So typically, you cannot solve those problems exactly, but heuristically using, for instance, affine decision rules. Okay, so that's one approach that has been used in the past. Another approach is heuristic by definition. So because min-max problem is complicated, the author of that paper, they define the worst case pairwise distance. So just an example, instead of taking the worst case position for the whole path, they would take the worst case position for every edge. So for this edge, U1, U5, you define the worst case distance. For this edge U5, U6, you define the worst case distance. At the end of the day, you don't have a true uncertainty point in your set. You define distance doing that. And then if you define those weights here, you can solve the classical mean optimization problem using whatever algorithm that you like. And if you solve that, then you return the optimal solution that you get. And they prove that for the if F is a Hamiltonian cycle, then you get a two approximation algorithm doing that. So this type of approach, we have generalized it a lot. I will give you some of the things that we have done, not all of them, because quite a lot. And the previous work that I presented, I will show you how it compares to our algorithm as well at the end of the talk. So this is a list of the contributions that are present in the paper. I will not present all of them. So we prove that some cases of the problem are hard. We provide an exact algorithm based on cutting plane. As I just mentioned, we study some extension of the approximation algorithm that I just mentioned, and we also have a FP task that I won't talk about today. So the NP hardness is quite classical in robust optimization to show that the problem, min-max problem, are typically hard if you have arbitrary uncertainty sets. Here it's a bit different because they are hard even in a case where normally they are not hard. Let me tell you what I mean. So it's well known that in robust optimization, if you have an uncertainty set that's simply a box, then this complicated problem, you just take the there's a typo here. There should be a bar over my C. Sorry about that. It's well known that you just take one point of the box that will be enough to cover the problem. So this problem is equivalent to the problem of minimizing just the worst case, and the worst case is this one here. Sorry about that. There's a typo. It should be a bar here. This is very well known. There's one dominating point in the uncertainty set if it's a box. So it's easy. So robust optimization with intervals or with boxes are easy. And what was interesting is that it's not the case anymore for our problem. So I will not detail the proof, but it's a reduction from partition using rather classical techniques. The only interesting point really is that it's hard even if you have intervals for every node of the graph. So even if the graph is really into R1, all nodes are in R1 and you have intervals for every possible position. And we have a similar proof for the spanning tree that's a bit more technical. And for the spanning tree particular, what's interesting is that the proof really use very ad hoc distances. You cannot use Euclidean distance for this second proof. And well, it cannot be deduced as a Euclidean distance. So it's a bit more technical. Okay, so now that the problem is hard, we want to solve it. So we will provide different type of approaches for solving the problem. The first one is a ILP. So this is a classical epigraphic reformulation that we see a lot in robust optimization. So if you have never seen it, it's not very hard. So initially we had min-max, right? Min over X and max over U. And what we did, we introduced the variable omega, and we said that omega has to be greater than this for every U in U. Okay, so of course, at the optimal solution, omega will take the smallest possible value. So omega will be exactly equal to one of these right-hand side, and which the worst case of them, of course. Okay, so this is what's called the epigraphic reformulation. And what's nice here is that, well, when U is fixed, this constraint is just a linear constraint with the binary variable X and the real variable omega. So this you can just feed to your favorite ILP solver. So the problem is, well, you cannot, of course, enumerate all points of this U here because U is a Cartesian product of the U for every set. So it's typically exponential in size. So you have to enumerate to generate a subset of those scenarios. So as this is quite classical in robust optimization, you have an adversarial separation problem where you want to find, given the solution X to your master problem, what is the worst case scenario for that X, okay? And that worst case scenario, if you find it, then you can create a new cut that you will add to your master problem and solve it over until there is no more cut added. That's a bit like Bender's decomposition that we have just heard of in the previous talk. And again, you can consider this separation problem either X is not a variable anymore. So you can even hide X in the structure F that you will be optimizing over here. Okay. And so we have studied the separation problem. So it so happens that the problem is hard. We can say a bit more than that. There is no p-task, so I won't detail that. But in some case, the problem is actually easy and can be solved by using dynamic programming. That's what is stated in the second theorem here. So actually, when the theory is constant, then the problem can be solved in polynomial time. And so I will give you an intuition about that for a tree, actually. And then using classical techniques, one can imagine how you generalize it. So why is the problem easy for a tree? So here is the problem defined for a tree. So this is our solution F, and every node of the graph, you have a set of points. And we will define this value function F for every node here. So let us, for the leaf, it will be easy. So let us start with this node U, for instance. And so what will be the value of this node U prime? Well, it will be the worst case of all possibility here and all possibility here, and that we will sum up. So that's what written there. The value function of U prime will be simply the worst case that you have for all sums, all nodes here in the red set, plus the value that we get by taking all nodes here in the purple set. And we just add them up, and you can go like that up to the root of the tree, and you get a polynomial-time algorithm. And that we have actually implemented in our experiment. I will show you the result of those at the end of the talk. If you have a very general structure that has a large tree width, this will not work. So instead, you could use ILP. So how do we do that? Remember that you want to solve this problem here. Okay, so you want to maximize over U here. And so what we do is we introduce binary variables. So binary variable yik will be equal to 1 if a node number I will be located exactly at position uik. And then if you do that, you get this quadratic assignment problem. So why do you have that? Well, this constraint here, they just mentioned that for every node of the graph, you have to choose exactly one position of that node. That's clear. And then here, this tells you that you will count the distance between uik and ujl only if you have taken yik and yjl. All other terms will vanish for node I and j. Okay, so that's not very hard to see. You can solve it using classical technique. It doesn't scale up as well as the dynamic programming, but it's a general tool that you may use if you wish. Okay, so that's all for the exact solution algorithm. So the type of a Benders decomposition algorithm. Now we'll give you some hints about the approximation algorithm that we have provided. So first, I will show you something that doesn't work and that may come up as natural. So, you know, when you solve problem under uncertainty, sometimes a naive approach is just to take the mean value in stochastic optimization, for instance. It's well known that in stochastic optimization, using the mean value is not very efficient. Let us see how it applies here. So here, the mean value would be taking the center of every set, what we call the barycenter. So on this example, for instance, what do we have? We have two edges. So that's a graph with two edges and three nodes. We have this node here, and this node here. So you have to imagine that actually the three nodes, they are located in R1. I draw it in R2 only for visibility. So this node, it always takes the value epsilon. It's in R1, okay? This node, it always takes the value 0. So the center is, of course, 0. And this node here, it takes either the value -1 or the value 1, which means that the center is actually -1 + 1, which is 0 again, okay? And so the problem we want to solve is actually choosing only one edge, one of the two edges. So it's a very simple problem, of course, okay? We just want to choose one of the two edges. So if we were to choose, if we were to consider the distance between the barycenters, then which edge would we take? This edge has a distance of epsilon. This edge has a distance of 0. So of course, we would take this edge here. Okay, that would be the solution using the average values. But of course, then in the worst case, if you take that edge, you get a cost of 1. While if you had taken the other edge, you would have got a cost of epsilon. So you see that actually choosing the cheaper solution according to the barycenter can be arbitrarily bad. Well, that's not so surprising. Very often in optimization under uncertainty, taking the mean value is not a good idea. What is a better idea is using the Dmax that I introduced before. So let me recall some notation that are already introduced, most of them. So what we want to solve is a problem for this cost function C of f. So the cost function that we want to handle is the one that considers the worst case value. Okay. And we will use instead another cost function because it will be easier to handle. And that other cost function take the worst case value pairwise. So you see the order of the maximum and the summation are not the same in the two expressions. So here for every edge, we take the worst case position. Okay. And so this defines the dij max that I described previously. And so the algorithm is the one that I mentioned already. So we will simply solve this problem. And we get a solution f max, and then we return f max. And what we can show, which is not very surprising, is that if you can actually bound the ratio between those two cost functions, then you get some kind of approximation algorithm. Let's be more precise. If you can say that for any f in your set f, c max of f is less than a given row times c of f, then you get that the solution returned by this algorithm is a row approximation algorithm. Okay, and the proof is actually very easy because so let us take f max as the output of the algorithm, this algorithm here. We take f star an optimal solution. Okay, so by definition, its cost is equal to opt. Then we have the sequence of inequality. So cost of f max is less than this one because c max is a function that's always greater than this function here. This holds because this was the optimal solution for this cost function here. And this holds because of the assumption of the theorem. So it's called a theorem just because that's an important point. And no large part of our work has been to devote to find a specific row for specific types of problems. So I will try to give you an idea of one general row that we found, sorry about that. So it's based on graph that are Ptolemaic. We didn't know what it was before starting this work. So let's just assume that it's Euclidean. Essentially, it works as you would think it was Euclidean space work. And so if you assume that your metric space, so the space on which the distance are defined, is Ptolemaic, then you get a row equal to 4. I will give you some idea of the proof. So the first idea is that we will define a specific subset U tilde of the uncertainty set that we had initially. Okay, and then for that specific subset U tilde, we sorry about that. Yes, so we have this cost function here that's defined here. Okay, then of course the maximization is greater than the expectation. Depends on the probability. Here we use uniform probability, for instance. Still true. Okay, then the expectation is linear, so we have this equality here, and then we can prove this inequality here. So we can prove that the sum of those average weight is greater than dij max over 4. And this is the tricky part that requires to do geometry in the plane. That's always a bit tricky. So, and that will depend also on the definition that we had given for U tilde. So actually for U tilde, we will take diameters of every set. So we have only 2 points in every U tilde I. Okay, so if you do that, having only 2 points, then this expectation here becomes a summation of only 4 terms because you have only 2 points, so 4 possibilities in total. And then if you do some computation and if you use the famous Ptolemaic inequality, then you can show that Ptolemaic inequality, then you can show that this is actually greater than dij max over 4. This is not very hard once you write everything down, but it's a bit tricky to explain it now. So this is for very general graphs. And so we could get tighter results if you assume to have specific charter. So if you have, for instance, that f is a clique, you get a row of 2. If f is a star, you get a row of 3. The first one was if you don't assume that your metric space is Ptolemaic, you get a 9 instead of a 4. And you get also lower bounds. So for instance, So for instance, for the star, I mentioned that the rho is equal to 3, and we can construct instances for which the 3 is actually reached asymptotically, because this formula is essentially 3 when n is large. And to do that, well, you construct this star here, and then you define those distances between those points. Okay, so the dot edges have a value of 1, distance of 1/3. The full one have a value of 1. And then you can see that here, because of the symmetry, you don't have many choices for the position of the adversary. The adversary can do that, that, or that, but the example is symmetric. So whatever it does, it's the same. And so the cost would be this edge here, plus twice those edge here, leading to 5/3, while by using Cmax, so the cost function where you can choose different points for every edge, then you always take the worst one. So you get a cost of 3, and by dividing the 2, you get 9/5, which is equal to that value here when n is equal to 4. Okay. So we have assessed those algorithms on some Steiner tree problem inspired by the literature. So we have compared the exact algorithm that I showed you a few slides ago. The affine decision rule, so I mentioned that in the first, when talking about the previous work, and the 2 heuristics that I just described, okay? And this is the description of the instances. I will not enter into the detail. Essentially, it's inspired by Stein-Lib, and we have some way to generate uncertainty sets. And so we run all of those algorithms. And what's interesting here is that the solution time, so mu, I think it's the ratio, right? Yeah, mu is the kind of the average ratio of the uncertainty sets. What's interesting here is that the exact algorithm, which is the pink one, is actually faster than the blue one. And blue one is only a heuristic because it's based on an affine decision rules approximation of two-stage robust optimization. So here we have an exact algorithm that is faster than a heuristic, which was a nice result to us. And also we have those 2 heuristics that are very fast because they reduce, they transform the robust problem into a deterministic problem. So here it's just a Steiner tree problem. So of course it's very easy to solve in the deterministic settings. Okay, so this is about the solution times. And now about the quality of the solution returned by the different heuristics. So essentially, the closer to a corner you are, the better you are. So for instance, the one based on barycenter, it's called center here. It's quite bad, as we had proved in the artificial example. So here it can be like 40 or even 60% larger than the optimal solution. So it can be quite bad. The so-called affine decision rule heuristic is actually very good because it's all nearly a 90-degree angle, which is not very surprising because it's well known in robust optimization that affine decision rules are very close to be optimal. Okay, so it's a heuristic, but it's a good one. And then the one that we studied theoretically, Dmax, is also quite good, nearly as good as affine decision rules. Okay. So that's all I wanted to say about the research that we have done on this problem. So now I will get back to the advertisement that you did initially, because I always do that when I give a talk. So as I don't know if many of you thought of that, but when I was doing my PhD some years ago, I was really fed up by the fact that there are like no free way to publish our work, although I was paid by the states, and you know the story, right? Most of us, at least in Europe, we paid by states. We work hard, we submit to journals, our colleagues have referee everything for free, and at the end of the day, you have to pay to get back your work, which is a bit weird. I always felt like that. So after some years, we finally tried to change things. So you may know that in other communities, there are many very good quality free open access journals. In theoretical computer science, for instance, there are many free conferences. And so we have created a journal 3 years ago, and it's not going so bad. So we have a bit more than 10 papers published already, and one of those papers got a very nice prize for the MOS Society. So it's kind of a sign of quality of the work we have published so far, and we will soon be indexed in Scopus, and we are also indexed in other databases. So if you believe that fair open access is a nice way of publishing your work, please don't hesitate and submit the best work you have. And well, that's all I had to say.
Okay, great. Thank you very much, Michael. So maybe we can take a couple public questions just before we move, in case some people want to ask something before they leave. So if there are any questions for Michael right away, please feel free to unmute or type in the chat. So I had one. So the ADR seems to do very well. I don't work in robust optimization, so I don't know the details. So you said it is known that's a good approximation, but when you mentioned affine decision rules in the kind of earlier in the literature review, maybe you said something about why they are limited. So that somehow doesn't seem to arise in your experiments. Is it just that they are heuristic, so there are no guarantees? And that's kind of.
Yes, the heuristic. I will just get back to the slide when they use. So here you have a two-stage robust optimization problem, and this is very hard because essentially lambda is kind of a function of W, right? And affine decision rules essentially say that lambda will be an affine function of W. So by doing that, you say that you don't accept every type of second stage variant. But it so happens that on many cases, it's very close to be optimal. Many people have witnessed that numerically.
I see, but then it's restricted to the Euclidean distance case. So yes. I'm wondering, is there another experiment that could be done with some other distance metric where this method is not applicable at all, and then basically only your method becomes the only option?
We have those results. I didn't want to present them because they're less interesting, I think. But yes, that's one of the advantages of our method is that you can apply to any graph-induced distance.
And in terms of computational efficiency, is there a reason why? So it seems eventually, I mean, both methods don't differ much in quality of solution, but since there's a bit of an advantage to ADR in terms of speed.
No, ADR is actually slower. That's what I mentioned.
No, but
here.
on the performance profile, maybe I misunderstood.
Sorry about that. I went very quickly on this one. This is not a performance profile. This is a quality profile. So
I see.
So the closer you are to an angle, the closer you are to the optimum. I didn't want to define it precisely. Just sorry about that. I went
okay, so you are getting roughly same quality solutions, but slower.
Exactly. ADR is very close to be optimal, but it's a heuristic, but it's very close to be optimal. And it's slower than the exact solution algorithm. That's the takeaway message.
Yeah, that's very, very surprising. I mean,
exactly. That's what
very nice result.
Yeah, thank you for your question.
Okay, great. So if there aren't any further questions, thanks, Michael, again. So now we'll do the usual breakout rooms